Right. So let me see. Well, screw it. Let me just put it from here. It's back in section 14.1, number 42. Let's see what this guy, how he's feeling. Oh boy. Alright. It's a bad sign. Yeah, it can still make it work for me. Yes. You don't want me to do what I call dancing. Alright. So, I mean, again, it's all messed up here. Oh, screw it. This is good enough. 42 in section 14.1, so they give you these. This is a contour map. These are level curves. And again, what do these numbers here represent? These fuzzy numbers here? Good, the z-value. So this is like just somebody taking the shape and going bam and just smushing it into the xy plane and just remembering how tall it used to be before it was smushed. So if you want to make this, it doesn't have to be a beautiful sketch, obviously. If you want to make a rough sketch out of this, so for example, this guy is 8 up. From this point in the domain, it's going to go up 8, right? So let me approximate where that is. That's going to be on the negative y side, right? And on the y-axis, you with me? So this point is going to go up 8 from right here about. And then where else is going to go up 8? About right here on the x-axis. Do you guys see what's happening? So that point on the x-axis, I'm going to go up 8 from it. You could be more precise with this, but I think it just says sketch. I can't remember. I'll use it, make it Bubba. So here we go. From out here on the x-axis, it goes up 8. Right, so it goes up 8, roughly there, and then here it goes up 8, right there. And so it makes this parabola. Weehaw! And then it's like 0 here. If you count in, it's 0 here. So it'll be actually on the xy plane here. This is the one curve that is actually where it's supposed to be, because that's a height of 0. So it's going to be like right here maybe. So it makes this parabola, bam. And let's do one more. There'll be another parabola down 6 from this point on the y-axis there. So down 6, maybe right there. Shpop. So then if I connect these vertices and I connect these sides, I get a very, 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 very rough idea. This poor little thing. I made this one way too freaky, but oh well. There, can you see? I mean, that's like this shape repeated down. As you move down the z-axis, it moves out along the y-axis. Wow! That's beautiful for me. That's perfect, right? Any better than this and you're showing off, but that's fine. Is that cool? I mean, that's all it really takes. You don't have to be that precise. You can be more precise if it makes you feel better. But that's really all I need. And you can describe to me what's going on. All right, how's that? Is that decent? Because there were some questions about that problem the other day. Yes?
Did we go over 104 and 14.3?
Sure. I agree with him. 104? Ooh, yeah. All right.
That's stuff that doesn't exist.
All right. So they tell us. Yeah. F of xy is the cube root of x cubed plus y cubed. And they ask us to find f prime, no, not prime, fx, is that right? Of 0, 0. So, first off, what's fx? What does that mean?
Partial effect. Partial.
Yeah, so what are you going to treat as a constant?
Y.
Y. So y is going to be treated like a constant, so it's like plus 7, or whatever you want to think of. So how do you take the derivative? So let me write it like this.
Squared over x, the 2 over
I like it. So it'll be 1/3 x cubed plus y cubed to the negative 2/3 times
3x.
3x squared plus
0.
0. I like it.
And the 3's cancel.
3's cancel, so you end up with x squared over this business. Now you don't, if you try to plug 0, 0 in, you don't exactly get something. What do you really get? If you try to plug 0, 0 in, what do you?
Not even infinity, you get 1 to 9.
You get 0 over 0.
Yeah.
I like it. So, yeah, what can you do? Yeah, so I mean, one thing you can do is now, if you do this, so are you guys saying to take out something from here? Okay. And so what would actually come out if you take an x cubed? It actually has to be, if you take an x cubed out, so you're left with this. What did you actually take out? X cubed to the 2/3 is x squared. I like it. So then you get 1 over 1 plus y over x cubed. Now, exactly.
Yeah.
It's not a bad try. I don't mind that. So you get 1 over 1 plus 0 over 0 cubed, right? So I mean, did that directly help you?
You do partial fraction.
So what form is this in? This is in the form 0 over 0. And derivatives are built off of limits. So what about taking the limit as I approach 0, 0? Do we know the partial derivative form of L'Hopital's rule yet, officially? No. So we wish we could. If you rewrote it, but then that would be too specific. It'd be like a specific path that you could rewrite y in terms of x along a certain path. That's too specific. Then you could do L'Hopital's rule all day because we know about a single variable, what to do. I like it. Just leave it like that, and hopefully Jeff won't notice. There's no real answer there. So I like this line of thinking. That's not a bad idea. Trying to kill the problem. You killed part of the problem.
Is it something to do with the fact that y is a constant in this case since we took the partial with respect to x? Is there something we can do with that?
Maybe.
That's the only thing I could think of.
Look back at the specific actual definition of this. And I mean go back to the limit definition that they have in the book. Oh. And I'm not, I'll start there. I like it. That's one of the last problems. You know it's going to be something freaky.
Is it even differentiable at 0, 0?
Well, that's really what we're investigating. Possibly the answer is it doesn't exist. Right?
And you can't prove that by using paths?
Yeah, if you could find two different paths, as this goes to 0, 0, if you could find two different limits that they approach, then yes. You could find counterexamples to show that it doesn't exist. But at the moment, it's indeterminate, which means we haven't figured the answer out yet. Right? Which tells me I've got more to do. If it was 1 over 0, that'd be awesome. I know what it is. It doesn't exist in a very specific way. It's infinite then, right? Infinite slope is fine with us. In fact, we have functions that are like closed that have infinite slopes. Yes or no? Yes? Okay, cool. Alright, so there's some stuff to investigate for that one. There's a really decent idea. I like the idea, but it didn't get us too far. But maybe this form is easier to use something on. I don't know. Anybody else try that problem yet? See, that's why I don't want to say too much, because not enough of you have tried it. Alright, so we give you a lot of things to try. So actually try to do it. Let me see. Before I get too far away, anybody else come in, didn't get their quiz back? Yeah, right. Jesse. I got stuff for you. Oh, cool. Oh, yeah. Let's see. Yep. And real quick, while I'm thinking about it, anybody need a copy? Wasn't here for that quiz, so wants a copy of it, so you see what it looked like. Okay. Cool. All right. Anything else from homework stuff? Maybe not the very last. Does every other problem go okay except the very last one?
Yeah.
Okay, that's a good place to be. All right. If there's no more questions, we're going to right back into it.
It's not continuous, right? Because it's going to be different from the left and the right. It's going to be a different value, right?
Yeah. So if you approach, if you let y be negative, is that what you mean? Approach 0, 0
From the left.
But see, this is squared.
I was looking at the.
Oh, over there.
Yeah.
Okay.
I thought it was approaching different.
But see,
numbers.
if you, I'll let you think about it. Say again. Yeah, I left it 2/3 out. Thank you. So it's the same thing, still squared, but this is internal. All right. So again, gave you couple major hints about this. This is indeterminate. You can think about it limit-wise. You can think about paths to show something. Yes?
Remember in the homework there was one where we had variables, and then you could set like y equals to x, and plug in x for that.
Of course, sure. But the only thing that's good for is to compare it to another path and show that they're different. Yeah. Single path by itself does nothing for you.
Yeah, no, it is different from the right and left, because if you come from the right, it's going to be basically 1/2, and if you come from the left, it's going to be 1 over 0.
Oh. Okay.
So it's not continuous.
So if everything we did here to there is legal in all senses, then this form should be a valid form to use.
Yeah.
So if you let like y equal negative mx and y equal mx, right? Or y equal negative x and y equal x, for example, right? This would be 1 plus 1 or 1 minus 1. Okay.
So it's not continuous. Which
So
means the limit
limit
doesn't exist, so the
of
derivative,
this as it goes to 0, 0 does not exist.
which means it's non-differentiable at that point. Cause
Yes,
it's
the
not continuous.
derivatives don't match.
Yeah.
All right. Well, shit. I don't want to give it away. Don't say anything else. We'll see if you were listening. It all depends on if you listen. It's amazing. All right. So last time we barely got into section 14.4. I got a couple of things to show you here real quick. This one's kind of cool. You guys, you can't see anything until I do this. Alright. So, let me do this first. Let me see here. I'm going to show the x partial from this point. So, that little dot, can everybody see? I can't really zoom in because it readjusts itself and says, screw you. Alright, well, screw you too. That point right there. That's the point I'm standing on, right? I got mail. If I show the x partial, so if I were to move in the x direction, that is the slope from that point. We turn around this way. Alright, so here's the x-axis. So this is what it looks like with respect to x. If I move in the x direction, I would go up from that point. Is that cool? So there's a question about what does this mean? And I'll have to turn you around in a second, but what does this really mean? Well, let me ask you two things. What does this mean computationally? What would I do first? Partial opposed to x. Because you can write it like this. So you need to get this before you can apply this to it. So we got the partial with respect to x. We got that sitting right there. But if I want to look at the partial of that with respect to y, okay, that gets a little bit weirder to try to capture it in a single image. Because what that would be is, if I were to then move in the y direction away from this, what would the slope, how quickly does the slope in the x direction change? So why is that steep right at that point? Because where I'm standing, that's how steep the ground is. If I want to move in the x direction, I'm going to go up that steeply from that point. Are you guys with me? If I move away from that point in the y direction, I am then asking, how does that slope change as I move in the y direction? That's what this really means. We've never had this kind of thing before because we never were able to do this kind of thing until we got to 3D. Let me turn you around so you can see this. People at home all sick. Sorry about that. Or, supposedly sick. We'll see what happens. So if I move away from that point, what happened to the whole thing freaked out. I like that. See, well, that doesn't really change much there. Let me change the point I'm standing on. Maybe something more drastic will happen. So right now, this would be big negative slope. So as I move along the y, it does change. Now here it's 0 basically. Fx would be 0. So it's all about, so what's happening? So right now that's big negative slope. Are you guys decent with me saying that? Because see how I just got it this way so I can see this easily? But you see how that's positive, that's negative? So as I move in the positive x direction, my height would go down. So as I move in the y direction from the point, what happens to my slope? Does it get bigger or smaller as I move in the positive y direction? It gets more positive, so it gets bigger. So then fxy should be positive at that point, because if I were to move in the positive y direction, my slope would get more positive, would get bigger. This is not the easiest thing in the world to, but I love this is it. This is the best I can do. I'm sorry. Thank God I'm not drawing this. When I take a second derivative, I am talking about how quickly the slope itself changes, of course. But now I can change that slope in different directions. Yes, sir? Yes, so it's more related to the twist of it instead of the direct concavity. If I do fxx, it means what it always means. Because then I'm kind of living in that plane. Let me see if you guys give me. So if I totally... Bless you. So I'm here. I'm going to change this. Boop. There you are, Jeff. So I'm there. This plane, where I'm sitting at on that point, if I just slice a plane through that, that's the plane that I live in. If I change the x, I'm just going to move along that shape. Is that cool? So fxx would be the exact concavity of that shape. It would be the same old normal thing. Fxx is really almost exactly the same as the second derivative in Calc 1. Not quite the same because my function still has y's floating around in it, but the interpretation of it is the same from that point. Because everything's in that one direction, that x direction. Are you guys with me? So if I change the x, like the x gets smaller, gets bigger, it just goes around that curve like I'm used to. So that's fxx. And this should be fxy. Woohoo! Yeah, dude. Sorry. All right. So if you're standing at a point and you're talking about what's the slope as they look in the x direction, what's the slope? Let me do it like this. In the x direction, what's the slope? But then fxy would be, okay, if I move over a little bit, what's the slope do? What's the slope do? Maybe it goes down, right? I'm like, I need to be over there. Let me go this, that's better. So I'm not, killing myself trying to climb there. You guys kind of understand? If you do any hiking or anything, you sort of understand what I mean. We can go that way or we can go this way. All right, it depends on what you want out of that day. You want to work out or do you just want a nice leisurely stroll? Maybe. Okay. The second thing I wanted to show you. Oh yeah, this is semi anticlimactic here, but this is what we're getting into, this idea of a tangent plane. So let me see if I can get a decent location for this. Bless you. Bless you. Alright, so here's a nice spot. Alright, so the tangent plane, it's basically, it's defined by the tangent line to this, see this green curve? So that's sort of like in the, they don't really tell me what this is, oh well, in this direction, right? So there's a tangent line, and that's the Calc 1 tangent line. Because that's just two dimensions there, right? If I just slice this way, there's a tangent to this green curve. Is that cool? There's also a tangent to this, don't they have one going the other way? Oh well, there's a tangent going this way. Is it the orange line? Is that an orange thing? Yay, okay, good. There's also a tangent to that orange line. That's the normal tangent that we're used to also. If I take both of those tangent lines, they define the tangent plane. So the tangent plane's got to be, no matter which way you go from there, the tangent plane must agree with where you would want to go based on the slope at that point. What's a tangent line mean? Well, it's like if I swung something around and let go, it's the direction that thing would head off according to the slope of it at the point where I let it go. That's the tangent line, right? That's the classic example. Oh, yeah. Wow, and you throw something at somebody. No, yes. Okay, I'm thinking about Xena, probably because I just watched Ash versus Evil again. If you're not watching that, show you first. Blah, 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 blah. Okay, so those are two quick computer-generated stuff I wanted to show you. It's way better than anything I could try to draw. So we're going to get into the nitty-gritty now about how to actually get the equation of the tangent plane. And going back to basics, what do we need for the equation of a tangent plane? Two things. Or of a plane, any plane. Normal. And a point. I love it. So the problem would tell me, find the tangent plane equation at this point to this surface. So the problem's going to tell me the point. So my part of it's going to be finding this normal vector. And actually we're going to work it to the point where we don't even have to find the normal vector directly. Let me put you away. That was leisurely. So, I should have put that away so soon. So we have this surface, oh boy, Jeff, in 3D. And we have this point, and we have a tangent in the x direction and a tangent in the y direction. So together they define this plane, and for me that's damn good. For me that's amazing. Okay, thank you so much for humoring me. All right. So we know that two vectors define a plane, as long as those vectors are not parallel. I like it. So these are obviously not going to be parallel because they're based off the x and y axis. That's beautiful. I love it. So we have this surface, I'll call it S. Yeah. And we have actually, and the book's got beautiful pictures of this. Let me just point out what pages they're on so you can, if you have the book, you can see them. Oh, book. Oh yeah, it was back here. There's a better picture back here. There we go. Beautiful. Page 956. And I think I slapped this picture up here last time. Oh, let me not do it again because I already took them away. So 956 has got the slicing the surface with a plane. So if I'm standing at a point X, Y, Z, so that's what this point is right there. That's the point X, Y, Z. I can then talk about the plane through that that's parallel to the y-axis, that runs through the y-axis. You guys got it with me? So if I'm standing on the surface, then I'm talking about the y direction purely. So there's a plane that'll run right through that. And that's going to create this curve of intersection. It's going to intersect that surface at some kind of a curve. Let me just stop there for a second. So if you got the book open at page 956, they got a beautiful little picture of this, the little blue curve. And that blue curve has got this tangent line. And the other curve, similarly in the x direction, has got the tangent line to it. I like it. So we call these, let me make sure I call them the same thing. Oh, let's see, what am I going to base it off of? This guy. Yeah, so this will be, this curve here will be C1, and this curve here will be C2. So C1 is kind of related to the X, and C2 is kind of related to the Y. And again, if you want a better picture than that, go almost anywhere, but definitely page, you can also look at page 968. That's a little more direct to the point.
Are you talking about kind of like the example you just showed?
Yeah.
Okay.
But again, it's if I have a surface, this always gets interesting. If I have this surface, I can slice it with a plane, and the plane is going to intersect it at some curve. So I can slice this with a plane that's related to, if I'm looking in the y direction, I'm doing Fy. So I'm only talking about moving from that point in the y direction. There's a plane I can slice that would define that part of the curve I'm talking about, right? So if I'm standing at a point and I'm talking about only moving in the y direction, then I've defined a plane with that statement. Are you guys with me on that? Standing on a point on a surface, I only want to move in the y direction. There's a plane that I'm talking about that I live in. That plane is going to intersect the surface at some curve. I can also talk about the x direction. It's going to intersect that surface at some curve. The tangent lines to those curves are what I'm going to use to define my tangent plane. It's crazy. I mean, it makes sense. The tangent plane should be made up of tangent lines. It's amazing. I like it. So let's actually make this more general. That's actually too general. Let's make this more specific. So we got x naught, y naught, z naught is our point. So we got that. So all we need now is like a normal curve, a normal vector. So let me just make sure. So I'm going to call T1, that's the tangent line, is tangent to C1 at P. So T1 is the curve, is the tangent line that is tangent to that curve of intersection at P. So that's like this line here. T2 is tangent to C2 at P. I like it. All right. So all about the point. We're all about the x direction. One curve element, that's the intersection, and the tangent to that curve. The tangent to the curve in the other direction. Cool. So what's the equation of a plane in general? What's the most useful equation of a plane? Yes? I love it. Cool. Now let me do a couple little things. Let me see if you guys are with me on this. If I let big A equal negative A over C, and big B, that makes sense, Jeff, equal negative B over C. So you see, what do you think I'm about to do? What would, obviously I'm going to probably do what to the whole thing? What do you see up here? I see an A. How do I make it negative A? Probably subtract it to the other side. So what I'm effectively doing, how do you solve for this? You subtract this over, you subtract it over, and you divide by C. I like it. So you would get this. Z minus Z naught equals negative A over C, so big ass A. Minus B over C, so big ass B. Alright, stop there for a second. You're going to love this. We'll find out.